Hello everybody, my name is Satoshi Hosihno. I am from Utsunomiya University, Japan. I'm going to talk about motion planner based on CNN with LSTM through mediated perception. For autonomous navigation as shown in this movie, first off, the robot is required to build a map of the environment. Then, the robot plans the path and motions according to the localization result in the map. In the right bottom movie, here you can see the localized position and planned path. If an obstacle is in front of the robot replans the path or plan the avoidance motion. So in this presentation, we focus on this motion planning in order for the mobile robot to move toward the destination while avoiding obstacles. This is an essential capability for the mobile robot. Motion planning is to determine a motion output AT, which is composed of the linear velocity and angular velocity Vt and omega t for sensor input St at time t. In recent years, motion planners based on deep neural networks have been proposed. These deep neural networks are used to determine a motion output for the sensor input. In other words, a deep neural network plays a role of planning policy pi. So the motion planning is represented as shown in this equation. We have thus far proposed motion planners based on multi-layer perceptron (MLP). Given a 2D LiDAR equipped with the robot, the range data was used as a sensor input. In previous works, the policies, which is represented by MLP, have been trained through imitation learning. In a framework of imitation learning, first off, desired motions for autonomous navigation, including obstacle avoidance, are instructed. After that, network parameters are optimized so as to determine the instructed motions as the outputs for the sensor inputs. However, the trained policies are highly dependent on the instructed motions for the obstacles known to the robot. So, it is difficult for the robot to plan avoidance motions suitable for unknown obstacles. For this problem, we use RGBD cameras instead of the 2D LiDAR. For image inputs, features of obstacles are extracted by using convolutional neural network, CNN. The motion planners based on CNN are categorized into two approaches, behavior reflex and mediated perception. In the former approach, behavior reflex, motion outputs are determined directly from the image inputs. For the image inputs with unknown obstacles, however, it is difficult for the robot to plan the avoidance motions. Therefore, we adopt the latter approach, which is mediated perception that utilizes a visual recognition capability. In this presentation, dynamic obstacles such as pedestrians are targeted in addition to static obstacles as shown in this movie. While the position of a static obstacle is fixed, a dynamic obstacle changes the position with time. So, it is important for the robot to plan the avoidance motions in consideration of the time series variation of the obstacles in the images. For this motion planning challenge, a long short-term memory LSTM block is applied to the CNN. The policy of the motion planner represented by CNN with LSTM is also trained through imitation learning. Here, let us explain the mediated perception process for obstacle recognition. The perception process is provided between the image inputs and the CNN in the motion planner. As an object detector, we use YOLO. So as long as YOLO recognizes objects in the images are all detected as can be seen in this movie. The bounding boxes of these static obstacles are colored by red. Here, two chairs here and here are detected as the static obstacles. On the other hand, these dynamic obstacles are colored by green. Of course, the robot can recognize both of them, even if static and dynamic obstacles are in the same image as shown in these pictures. Now, let us explain the proposed motion planner through mediated perception. First off, an RGBD image represented as iRGBD is captured by a camera sensor. Then RGB and depth images are generated from the RGBD image. The depth image is directly fed as the input to the following convolution and pooling layers. On the other hand, a perception image is generated from the RGB image by the object detector YOLO. Then the perception image represented as IP is fed as the input to the convolution and pooling layers. After that, extracted image features are flattened and concatenated into the fully connected layers. In the third layer, the linear and angular velocities of the previous step are fed as the input here. Moreover, an LSTM block is applied and the goal direction is further fed as the input here and here. Finally, the velocity and angular velocity, Vt and omega t, are determined as the motion output. For autonomous navigation, we use this mobile robot as shown in this picture. The maximum linear velocity is 0.5 and reduced to 0.4 for obstacle avoidance. The maximum angular velocity is 0.8. The robot is equipped with 3 RGBD cameras, a front, left, and right, and 2D LiDAR here. The 2D LiDAR is used only for adaptive Monte Carlo localization. For comparison, 2 motion planners are applied to the robot. One is based only on the CNN without LSTM, and the other one is based on CNN with LSTM. Please refer to our paper to see more detailed structures of these motion planners. For motion instructions, we provided this kind of environment. In this environment, the robot is instructed by a supervisor with a joystick controller to move from S toward G while avoiding obstacle O. Both the standing and walking persons are detected as the dynamic obstacles. And the robot is instructed move to avoid the obstacle as can be seen in these movies. During the motion instructions, the robot registers the sensor inputs and the instructed motion outputs. These datasets are used for imitation learning. Here, let us compare the imitation performance of the CNN and the CNN+LSTM, focusing on the instructed linear velocity. For standing person, CNN+LSTM was more consistent with the instructed velocity, especially when the robot reduced the velocity for obstacle avoidance here. As a result, the average mean square error, MSE, of CNN+LSTM was less than that of CNN. For the walking person, both the CNN and the CNN+LSTM resulted in almost the same performance. This was because that the duration time for obstacle avoidance was decreased, as shown here and here. The robots based on the motion planners repeated 5 trials, 5 times in total. For the standing person, the robot reached the destination in all the trials. The average relative distance when the robot began to avoid the person was almost the same, 5.1 and 5.2 meters. For walking person, the robot based on CNN stopped emergently before avoiding the approaching person and rarely reached the destination. As for the remaining success cases, the average relative distance when the robot began to avoid the person was 3.2 meters, whereas the robot based on CNN+LSTM kept a distance of 4.4 meters. For your information, let us show you the robot moving toward the destination autonomously. In the left, the robot based on CNN failed in avoiding the walking person. In the right, the robot based on CNN+LSTM successfully moved toward the destination while avoiding the walking person. In order to discuss the avoidance motions depending on the motion planners, we focus on feature maps extracted from the depth images when the distance to the walking person was about 5.5 meters and 4.0 meters respectively. In the feature maps, white pixels here indicate the attention area in the depth images. So we can see that the robot based on the motion planner of CNN paid more attention to the walking person here and here than that of CNN here and here. In other words, these results indicate that the robot successfully considered the time series variation of the obstacle in the images by applying the LSTM block to CNN. As a result, the robot reached the destination 4 times here. Okay, in conclusions, we propose the motion planner based on CNN with LSTM through mediated perception. As a result, the robot was enabled to recognize known and unknown objects as obstacles, consider the time series variation of the obstacles, and extract the collected features from the obstacles. These results indicate the effectiveness of the proposed motion planner for autonomous navigation, including obstacle avoidance. Okay, that's it. Thank you for watching.